Hi, my name is Augusto Jang, and this is my lab report video for Lab 3 for Physics 2211. So, a brief introduction. This lab is aiming to explore movement caused by gravitational forces, um, and obviously, this would explore Newton's second law. And in this lab, we're exploring a black hole system for part one, and a planet-moon spaceship system for part two. So the goal for part one is to find the mass of the black hole from the star's motion from the starter code that is given, and the goal for part two is to find the initial velocity that will make the spaceship orbit around the planet and the moon in an 8-figure orbit. So some of the concepts that are covered for this lab are obviously Newton's second law, um, how net force equals change in momentum over change in time, gravitational force, which equals gravitational constant times mass of the source times mass of the system divided by r squared. And for part one, the source would be the black hole, little m would be the star. And from that equation, we can see how the black hole mass can be calculated by getting the magnitude of F net, which in the fourth bullet point is just called F, timesing it by r squared, and then dividing everything by g times m. So for part one, the code, as you can see on the right, I calculated the star's velocity from the position. I found the momentum and change in momentum. And I used dp over dt obviously to find the net force according to our formula, and then we solve for m. And this code prints the values for m, and from all those values we found the average to determine the mass of the black hole. So from the results for part one, as you can see, the average mass for the black hole, there's a lot of time intervals and a lot of recorded masses, so I couldn't show all of them, but the final average mass was 1.23 E34 kilograms. So what does it mean? Answering the question from the lab, the rate of change of momentum represents how quickly the star's motion changes, and it's the net force acting on the star. The parallel component of dp over dt represents the changes, no, that changes the magnitude of momentum. Um, yeah, like the speed along the orbit. The perpendicular component changes the direction of motion, and the net force combines both of them. So it maintains, if you're doing an orbit, it maintains the speed you're going to, like for example, and then continuously pulls the star inward. Moving on to part two, the given, where planet is fixed at origin with that mass, E8 E27, the moon's mass, moon's spaceship's mass, gravitational constant, and delta t. So I found the initial velocity is kind of guessing it, and obviously too high of a velocity means the escape. Too high of a velocity will mean the spaceship will escape the orbit. Too low means it will crash on the planet or the moon. And those were the values I got that made me get the orbit. So for the results, as you can see, the spaceship takes turns being pulled by each body, creating the looping 8-figure. Obviously, the orbit, as you can see, is not completely perfect, but it demonstrates the right concepts in gravitational relations. For the what if part, To predict motion in a system with a black hole, star, planet, and moon, the model must include gravitational forces between every pair of objects. The black hole's gravity would dominate the system, controlling the overall structure of the orbits, and the star would orbit the black hole, while the planet and moon would orbit the star, but all slightly perturbed by the black hole's strong pull. And smaller interactions, like the planet-moon and star-planet, still matter, but the black hole's force is the most significant overall. And thank you.